Alright, so let's kind of do another quick review of what we saw about the last couple of days. So we started off on Monday talking about continental drift, right? So when Alfred Wegener goes around, he's finding all these evidence that at one point in time the continents definitely were together, and then they've been slowly drifting apart, spreading apart. And the problem with his theory is that he couldn't explain how or why, right? That's basically the gist of Monday. You know, all these evidence, you look at fossils, look at rocks, looked at the edges of the continents, and realized they all kind of fit together. Well, what he was unable to do was actually look at the ocean floor and get evidence from there. And that's the whole point of seafloor spreading. That's where that theory comes in and finds even further evidence for continental drift. And we basically come up with this theory of seafloor spreading that basically says that new crust is created at the ridge and destroyed at the trench. That's basically what that theory states. Very, very simple. So we look at seafloor spreading. We look at it in a lot of different ways. We look at the age and the depth of the sediments. We look at the features on the ocean floor that we get from sonar. And we also looked at the magnetic field readings that we got from the magnetometer. And when we look at these, they're basically really two separate theories. You have the theory of continental drift, and then you have the theory of seafloor spreading. And they really are two very different theories. And although one can be used to even further the argument for the other, they don't necessarily explain the whole theory of how the plates are moving. And so that's where we get the theory of plate tectonics. So again, remember, this is something that was put together in the late 60s. And we are still finding more and more evidence to support the theory, but it is still a theory. Keep that in mind. It's still a theory. And basically, when we think about plate tectonics, we have to understand that the Earth's upper crust is made up of these big plates. So the upper mantle of the crust are these gigantic slates that are the continents and the plates themselves. So the oceans actually are a plate. We have the Pacific plate, which is one giant oceanic plate. And these things are just spreading around the Earth. It's kind of like having the floating candles in a pool. Occasionally they'll kind of come together and then they drift back apart, and then they come back together and they drift back apart. And this has been the story of Earth since the beginning of time. This is just what they do. They come together and fall apart. And as we saw on Monday, when we looked at the continental drift, we saw that animation. And one thing you guys notice is that the plates are moving in different directions and at different rates. So we're going all over the place. Not necessarily going in the same place. We're not always moving in the same direction. Nor will be drifting at the same rate. Some plates are moving much faster than others. I remember we saw the Indian plate flying through the Indian Ocean and eventually landing into Asia. That's a pretty fast moving plate, as was Australia. Now the collision between these plates, this is where you have to understand a little bit about physics. You have to understand a little bit about force. Take two very, very small substances. How do you create a big collision with small substances? What would you have to have? A lot of speed. Okay? Which is why we're trying to look at the Hadron Collider. We're taking very small particles. We're taking protons and speeding them out to ridiculous rates and slamming them together. Okay? That's basically what the Hadron Collider is doing. So I said they're small. How do I create an equal collision, but with really big items? How do I create a collision that's just as powerful, but with really big items? Yeah, you just have to push them together, but would they have to be going as fast? They need more force. Okay, so Well, actually, if you have something really massive, the speed, the bigger you are, the less speed you need to create a very large collision. And basically a lot of energy is released because of the mass. Okay? Keep in mind that force is mass times acceleration. So even if you have like a super large mass, it really doesn't need to be accelerating that much to provide a tremendous amount of force. Okay? It's like the difference between being hit by a smart car going 70 or being hit by a semi going 40. Tremendous difference in their speeds. Definitely you're going to feel the semi a little more than you would feeling the smart car, which is pretty much nothing more than a cool car. So that's kind of what we're talking about here. So we have these plates, and they are moving tremendously slowly, right? You guys found that out yesterday. What's the average rate of split in the Atlantic Ocean? You guys remember that? How fast is the Atlantic Ocean opening? Think back to the lab you did yesterday. Yes, 2 million years. It's opening based on how far did it move? What? Yeah, do you guys remember that? You had to find out the rate of expansion in the Pacific, the Atlantic. Yeah, it's like 3 or 4 centimeters per year. Okay? It's about the same length as your fingernails grow. So imagine how far your fingernails will grow in a single year. That's about as far that the plates are moving. Okay? So they're really not moving that far. But because they're so massive, they pack a lot of energy when they collide. And that's where we get earthquakes. That's where we get all our volcanoes that erupt. So when these things do collide, we get really, really nasty outcomes. And this is probably an important one for you guys to know right here, is this is kind of a new term, which is not something that's like, wow, I didn't realize that. Plate boundaries, right? Okay, so plate boundaries is just where they're colliding. And we have 3 different types of plate boundaries. What are they? That happens on one of them. Abby?
Aren't they like convergent, divergent?
Yeah, what's that third one? All right, so convergent's one of them. So converging boundary, divergent. What does it mean to converge? Yeah, we're coming together. Two things are converging, they're coming together. What does it mean to diverge? Go apart. Okay, and then the other one is. It's the one that slides, yeah. So let's actually take a look at these.